stored to the cloud. In the meantime, I will check on how much extra credit we have so far. I think you guys are at like 50, so you probably already got the half a point. But if you get to 90, that is a full point. Let's see. Here. Yeah, I guess that's average. It's like a 45, but yeah, round up to 50. So yeah, you're pretty much at 50. And then if you can get to 90, I'll add a bunch of extra. Yeah, so this is like, of course, like before Rich adds extra credit, because usually at the end of my classes, once Rich does his like final grade or whatever, you'll probably get more. Yeah, 90%. Okay, I will get started. Let me start with, before I get into some nerd stuff, just cause, let me talk about the system first. And also let me figure out how to not have it by sound. There we go. Okay, so this is our system. This is like a little motor and it's connected to a little power supply. And so when we turn this motor on, this thing, which I have a picture of right here. So when we turn the motor on, this thing will spin a rod and this cylinder right here will spin around. The way that it does something is we put this string, you'll use, so this like golden string is stretchy, and either white or orange string is not stretchy. You can just test it by stretching it. And so what we do is we put it through this little axle here. And if you notice that the axle is not attached directly in the center of the spinning thing. And so as this spins around, it will move in a circle and it will push the string up and down. And so that's what happens here. This goes effectively up and down and it moves the string up and down. And so we send vibrations along the string. The way you set it up is you kind of feed the string through this axle and then through this hole in the post. And then you can use your binder clip to kind of secure it, or you can just tie a knot. It really doesn't matter. The only issue with tying a knot is that you have another string to do, but it doesn't really matter. So let's get rid of that one. Let's look at some more stuff. So yeah, so that's what it looks like once you're done. You put it through this one, put it through that one, and then secure it with the tool. And all in all, it looks like this. So this is a real life version of that. And what's happening with the photo gate is as this is spinning, so this is in action, you can see it's kind of blurry right there. Attached, like welded onto the side of the cylinder is pretty much like what a flag is, like on our carts, that flag that was being caught by the photo gate. And so what you're gonna do is set up your photo gate using, there's a screw right here that you can increase or decrease the height. You're gonna set it up so the laser comes right over the top of the cylinder so that the flag makes the light flash. So it should be blinking on and off. And what that does is it tells us the period with which we send things down, like how fast we're sending the waves down. I'll get into that in a minute. So the data that you get from Logger Pro looks like this, where all of these are pretty much the same value. The reason for that is there's no like friction like last time. It's literally plugged into an outlet. So there's just a constant voltage being applied. And so these numbers are all practically the same. You can just choose one of them when it asks for like period. You can just choose one of them. Let's see, that is all good. Let me get into some math first because I wanted to explain why I took such a long time to do the intro last time. And I want to explain that Hooke's law is really like the whole reason that this equation is here is really just to make the point that the simple harmonic motion that we did last week is the way that we find all of these equations. So the way that we find this equation and this equation are by using Hooke's law in a variety of circumstances. So the first thing I want to mention is how that goes. So instead of like last week where we had 2 springs and 1 mass, imagine that there's like an infinite chain of masses and an infinite chain of springs. As you kind of, it's like plucking one on a guitar string or whatever, the wave, so one of these things, so instead of like last week where we were oscillating in the X and I guess, yeah, just call it the X direction. Now we're oscillating in the Y direction because remember our motor is going up and down. So what we're doing is we're flicking one of the masses. So you can just imagine like all along your string. And this is really like the fascinating thing is this is really how modern day research is done. Like everything from the desk to this string is basically just a mattress with a bunch of springs and masses connected to it. That's really how people for the last 100 years have been looking at matter and how like everything from how electrons move to how we do superconducting and all sorts of crazy stuff, quantum computing, like a ton of stuff is just made from this basic assumption that matter is like this mattress here. And so what happens is as we pluck one of the masses, it creates like a wave, like people in a stadium or something. One person puts their hands up and then the next person puts their hands up and the next and so on and so forth. So instead of oscillating just up and down, which was characterized by the time, this is what we did last time. Remember, I just had some function with time dependence. Now we're including space dependence. This K is what's called the wave number. For now, you can just think of it as some variable. Remember, this angular frequency, I kind of defined it in an ad hoc or just willy-nilly way last time, and it really only ended up telling us about the speed of the wave. Now it's kind of telling us how quickly or how far the wave traverses, because it's dependent on something called the wavelength, which is, well, wavelength is like the length or distance version of the period from last time. So remember, it's kind of cut off here, but the omega is related to frequency and frequency is related to the period. And the wavelength is the distance it takes for something to complete one of the wavelengths. So let's see if I can find a good image here. Not really. But anyway, you can just see a period from looking at a graph. So this is like, you know, when the spring was at its equilibrium position, it swung out to the right, and then it came back and go to the left. And the period of the oscillation was how long it took for it to repeat the same action. So it's coming back, going left, and here. So our period is from here to here. Or as they mentioned in this graphic here, you can either measure from the 0 to the 0, or you can measure from a peak to a peak, or from a trough to a trough. It's all the same thing. These are all in, so this is in space, a wavelength, but in time, it would be a period. Okay, so now we understand the intuition behind this. This is kind of that vocab word I used last time, the ansatz, like my guess for what this function x was. Because remember, I wanted to find something that gave me a second derivative in time, something with a negative, and the function itself. This time, I need some kind of derivative in space too, because this was time. I knew my thing was oscillating in time, but now it's oscillating in space as well. And the way we guess that, it's not so easy what kind of function it would look like. what we do is Hooke's law. Hooke's law in a very, I'm not going to go through all of it, but it's like, where is it? It's like instead of Hooke's law for just one mass, so F equals negative kx, it's Hooke's law for a bunch of masses. And we use this principle called superposition, which turns out is kind of the backbone of quantum mechanics as well, which is why waves and light and all that things is the kind of go between classical physics and quantum physics. Basically doing the math and keeping track of everything for a bunch of masses instead of just one, like we did last time, we end up with an equation that looks like this. I think it's easier to think of H as just a displacement. Did I write it more succinctly? Right, so in this notation here, like that, this is really just thinking about the change in some variable. So ours is like y, for instance, because we are looking at, oh, I deleted it. We're looking at things going up and down in the y direction. So that's why they're writing y here. And that's why, similarly, we write y. We're thinking about the vertical direction. But the funny thing is that when we write this out in terms of this derivative language, this is actually the exact, so if we, this is purely from Hooke's law, this displacement. So x is like the equilibrium position, h is like some displacement away from that. This form, or this kind of function or combination of variables right here, is the exact form of what's called a second derivative in space. So this is like, it's a little bit too much to go over right now, but I'll do it in the one derivative case. So notice this like double prime here is taking two derivatives. So it's kind of like what we did with time, but in the space direction. Instead of doing two, let me just do one. And it's really the formalization of maybe something I mentioned early in the class where I was comparing slopes with derivatives in terms of like position and velocity and stuff. This is the formal definition of a derivative. You change the function a little bit. So the function at some, f is the function, x is the variable. We change x a little bit. So this is like our rise. This is like the rise of the function. And this is like the run of the function. So this is like a slope. The actual like formal definition of going from like a slope to a derivative is taking the limit of a very small run. So letting this limit go to 0, the effect of that is taking some finite quantity. So this is like, I don't know, 2, and this is like 0.000002. And that is the definition of a derivative. It's just a slope at a very, very small exact location. And so generalizing this to two derivatives, that comes exactly from looking at Hooke's law. So looking at Hooke's law gives us something that is exactly the same as, so instead of right here, we're just looking at like displacing the mass just a little bit. And it turns out that that is exactly a second derivative. And so what ends up happening is we have, instead of second derivative in time equals something and the function itself, now we have second derivative of time, some number, and the second derivative in space. This number turns out to be the speed of the wave, and I'll explain that in a little bit. So here, what I'm doing is instead of making just like a guess that the thing oscillates in time, like last time, I'm going to include space. The way that you get from this equation to this equation is just trig functions. So if you look at trig sum, it's a very common thing to use in physics. That the sine or the cos or whatever of two things can be written as expanding them like that. And what happens when we do this, because they're symmetric functions, or symmetric and anti-symmetric functions, basically what I can do is write that, and I can separate the spatial dependence and the time dependence into one equation. That's why this looks so nice, because what I can do when I take, this makes taking my derivative easier. Because if I take the time derivative of this, I get the same thing I did. Oh, I just deleted it. This is the same thing that we did 2 weeks ago. This is the new one, but it follows exactly the same way as time. It's, they're still signed, trig functions. So the second derivative with respect to space, x right here, is just negative k squared. The second derivative of time is exactly what we did 2 weeks ago, negative omega squared. So then I have this thing, this velocity of the wave is what I'll call it, squared, negative omega squared and negative k squared. Cancel out the negatives, cancel out all the squares, and I'm left with the velocity of the wave is the frequency of the wave over this thing I defined as the wave number. So that's 2 pi over the wavelength, or how long it takes for the wave to complete a cycle. Then remember from 2 weeks ago, this definition of angular frequency, I can write that as 2 pi, the regular frequency, and plugging this definition back down into here, I have the regular frequency over 1 over the wavelength. And so rearranging this, velocity of the wave is equal to the frequency of the wave and the wavelength, which is exactly this equation. So that is why Hooke's law is like kind of the backbone of where waves come from, and from waves you get quantum mechanics and special relativity and a whole bunch of crazy stuff. So waves and harmonic motion is really like the springboard that launched the last 100 years of physics. This comes from just a bit more intricate bookkeeping of this picture. It comes from thinking about how much force you're putting on one of the masses when you pull it up, as well as the spring constant. So let's see, do they cover it here? No. I think it's in this textbook, in classical mechanics. Wave equation for a spring. Yes, like this. It's way too much math to go over right now, but it's basically a more intensive keeping track of how the forces that go on with like a force diagram like this. You have tension pulling on the spring in one direction, tension pulling on the other direction, and the way that mass is taken care of in the spring sense, is through this quantity mu. Mu is the mass of the string in one particular segment and divided by the length. So it's like the mass density, yeah, here it is, mass per unit length. And so that's where that comes from. This is just this is purely classical mechanics. This is like wave mechanics. The only other things that come up in terms of like equations like this, this equation 5 comes from 3 using this equation 4. And the way that 4 arises, it's actually explained very well here. But the way I can explain it briefly here is with is like this. And this is covered much more in depth in that YouTube video that I posted on the announcements. I think this is Khan Academy maybe or something like that. But it basically comes from the fact that we are stopping our wave doesn't oscillate forever. It has 2 fixed endpoints. And so those are what's called like nodes. Nodes are like points where the wave destructively interferes. And so in enforcing that, we know that the wavelength must have something to do with the length over which the whole thing oscillates. And it turns out, it's explained pretty well here, that the length must be some number divided by 2, the wavelength. Because we see here, in this picture, it's easiest to see, this length is exactly 1 wavelength. Because the thing is going down, now it's going up, and now it's going down again. So this is exactly the same physics as what's going on here. This one is not. It needs to go up, down, and it would come over here to be up again. That's why the wavelength would be 2 of this whole thing. And so that's why this, this relationship here comes. The wavelength is 2L, so 2 times the length of whatever's oscillating, and the number of what exactly do they call that? And it's not quite nodes, because you see there's this relationship here. So for instance, n equals 2 is really just 1 node. So a node is like these points of destructive interference. So this would have 1, 2, 3 nodes, but it's called n equals 4. And that really just follows from this equation right here. And so if we plug in this relationship we just found, which is generic for something of fixed endpoints, if we plug it into here and reverse, some of the orders around, we find, and the reason we do this is because this, we could have, they could have made it harder for you by just plugging in V equals F omega, plug that in for omega, and just give you V equals F 2L over N. The reason they do it here is just to make it a little easier for you, because this is exactly in the form Y equals MX. So the whole point of the first part of the experiment is to theoretically get the value of the wave velocity, which we get purely from this like Hooke's law bookkeeping. So we have tension and the mass density of the spring. Tension comes from the hanging mass. So we have a hanging mass, gravity. The density of the string comes from the mass of the spring over the length of the spring. And this figure here, not quite. Let's see, it's in here somewhere. Yeah, there it is. So this is the length over which it oscillates, but the full length of the string is delta L and regular L. Let's see, do they explain to you what that formula is? No. Anyway, the formula is L prime. So this is the variable in your lab sheet, the length of the string. Really, you should just call it the total length of the string. This is what's like being oscillated, and this is what's hanging like past your pulley or whatever. And yeah, so the way that you calculate mu is the mass of the string and the total length of the string. So what's going over your pulley plus what's hanging on the end. And so the objective, let's see, I think this is all done. Yeah, I can get rid of that. Yeah, so the objective of part 1 is to calculate, you don't need to turn on your motor at all for this one. It's just measuring the string, measuring length, weighing things. And this one you turn on the motor. And this is why they made it easy for you, because this is already Y equals MX. You have Y, X. So X is what you're changing. You're turning the knob on your motor, and more nodes appear as you go to different periods. And these frequencies are what you measure from log effect. You measure them via getting the period, and then frequency is just 1 over the period. And then this is your slope, and your objective is to get V. So it's V theory, V experiment, and do they match? And then part 3 is seeing if your theoretical mass density matches. You take one of your non-structured strings, weigh it, get the length of it. This should be L prime. I don't know why I kept forgetting to write that. And then you get the experimental part of the mass density. So the way that they do that is they take this equation, but they plug in V. where is it? No, B up here. So what they're doing to get this equation, again, they made it easy for you. This is Y, this is M, and this is X. Where did I put that? I could have sworn I wrote that out somewhere. Yes. So if V is equal to the mass of the string, I'm sorry, hanging mass, gravity, tension over mu, and I plug that in here, then I have square root mg mu. I square everything to get rid of the square root. So I have f squared. I'm just bringing that n right there up in this numerator, n over 2l squared, mg over mu. Then I arrange it like they have in the lab manual. So m is my independent variable. That's me hanging more mass on my string. F squared is what I get from logger pro. And then this is my slope. And what I do is I rearrange that m equals this equation to get mu. That is our game plan. And I think that's all I need. One thing you might want to take a screenshot of, a lot of people were not understanding this one yesterday, was the uncertainty of V, at least the theoretical one. And the key thing to realize here is that you can write a square root as something with an exponent of 1/2. And so once you have that, this is like a quantity A, this is like a quantity B, and so you use equation 10 for the error. And then inside equation 10, you have the uncertainty of something to the 1/2, which you can use equation 11 on, where instead of the normal 2 that we usually have, now n is 1/2. So 1/2 minus 1 is negative 1/2, which means you put the square root like up here in the denominator. So that's how you get that. I think that's it. Yes, frequency is 1 over period. Period comes from logger pro. Yep, that's it. Okay. I'll stop sharing and post it on Blackboard.